Working? Hello. Okay, hi. Thanks for bearing with us while we figured out how to set up the Zoom. This is the vague order of events that we're going to try to aim for. Maybe take off 7 minutes from each of these because we took a little bit long. So if you need to leave and come back, we're going to be here until like 9. And if it goes over, we might stay a little longer.
Just open the Zoom.
Silence. Also, we're gonna post these slides on Ed afterward because I have the answers to questions we're gonna ask you in it. So.
You see. Yeah. Exactly. Wait. Where's it? All right, cool. Hello, everybody. Thanks for bearing with us while we took a bit to figure out the whole situation. Okay, so we're going to start by going through some review of the pre-quiz material, just like general, like how do we prove some things and general logic, things like that. So if you remember, like what we want to do, if we have, let's say, P and Q, and you need to show that P is true and Q is true. Well, to do that, like in a proof, you would actually, we want to show that both things are true. So you could kind of break down separately and show like P is Q and show and show Q is true. For like a logical OR, so fancy, yeah, sorry. For a logical OR, this guy, we basically want to conclude that like P or Q is true. So we could kind of break this down and we could say, okay, if P is true, then this whole thing is true. And if Q is true, then this whole thing is also true. Let's say we have something that's for all quantified. So how do you show something that's for all quantified? Well, if you remember, what we want to do is we want to take an arbitrary element in the set. And the reason for this is that we want to show this is true for every possible element in the set. So we can't really like assume something specific about a specific element. So what we do is we take any arbitrary element in the set, and this could be anything. And the idea is that if we can show it's true for just this arbitrary element that we assumed nothing about, then we could kind of conclude that it's going to be true for like every element in the set, since basically the only thing we assumed about this element is that it's in the set A. And if you remember this P of A thing here, this is a predicate, just some arbitrary predicate that takes in, you could think of it as like taking in A and quote unquote returning like whether it's true or false. So the other quantifier we have is an existential. So like there exists some A such that P of A is true. And if we have to prove this, well, the statement is just saying there exists some A, as long as there's one. So you could kind of also read this as like at least one. So if we want to show that like at least one A makes this predicate P of A true, then we could kind of construct or find just like any arbitrary A. So this is kind of where a lot of times we'll kind of take like a concrete example. So if we want to show like there exists an even number, well, you could say, okay, well, here's 2. 2 is even. Therefore, there exists an even number. A lot of times we'll use this when we want to show a counter example, which I'll get to in a little bit. And then for a biconditional, this P if and only if Q. Well, what this is basically it's P implies Q and Q implies P. So if we want to show this if and only if, we can show these two directions, P implies Q and Q implies P. You can also do like a chain of if and only ifs, but I feel like that's not too common. So I would say like knowing this kind of breakdown is more useful. So what about an implication? So there's a few different methods to prove an implication. So we have the direct proof, which is where we can assume P is true and then show that Q is true, assuming P. When you have an implication like this, really your want to show is Q. So you could kind of just focus on like, okay, I want to show Q and trying to derive Q, like trying to get everywhere to show Q and then using your assumption P wherever it becomes helpful. Another method of doing an implication is the contrapositive. And if you remember, contrapositive is basically not Q implies not P. So to prove a contrapositive, we basically prove this implication here. And you can do, so before in the previous slide, we talked about the biconditional here, this if and only if. So if you were to use a contrapositive for like a biconditional, you'd use the contrapositive here for either of the directions or both of them if you so choose. Another method we have is like a proof by contradiction. And when we have a contradiction, or when we wanted to use a proof by contradiction, we essentially want to prove that the implication doesn't hold, or assume that the implication doesn't hold, and then derive some contradiction. So it's like if we assume something is true, and then go step by step, making kind of small steps and deriving some other information from this assumption, and we get something that's like totally not true, totally false, that's essentially the contradiction. We derive a contradiction, and then because of that, we say, okay, then our initial assumption must have been false. So basically, we assumed that the implication was false, and now we got some weird contradiction. So therefore, our initial assumption was not correct. So that means this thing, P and not Q, which is not the implication, is false. So it's basically like going a little in reverse in a way. Like we're kind of assuming the opposite and then deriving something that's false. And when you have like an implication like this, it may be helpful to kind of break down your assumptions. And what I mean by that is, let's say we know that P or Q is true, and we're trying to show R. So in a case like this, the way we prove this implication is by we assume this is true and then derive that R is true. So this is kind of a more involved assumption here. We can do P or not or Q. So what we can do is we can kind of break down into cases, say like case one, P is true, and then derive that R is true. Or case two, like Q is true, and then derive that R is true in that case. So you could think of proof by cases as making it easier to prove something by kind of splitting things up into assumptions that are easier to work with. So to disprove something, what we're essentially doing is proving the negation. So if we have like P and Q and we want to prove that that's false, then what we can do is we can prove the negation of that, which is not P or not Q. If you remember, this is De Morgan's law, and it basically says like exactly what's written up there, that P and not P and Q is the same as not P or not Q. And likewise, for if we have not P or Q, then we could get back to we can prove it by showing by proving not P and not Q. So what about kind of these quantifiers? So if you remember, when we negate a for all, if we negate a for all of something, we're going to get back like the existential quantifier. And likewise, if we do negate the existential quantifier, we're going to get back the universal quantifier, this for all thing here. So if we want to negate something that's for all, then we get back this existential. And a lot of times this will crop up in basically what we call a counterexample. So a lot of times we'll have some kind of proposition that's like, for all elements in the set, some fact about that is true. And if you want to disprove that, you can just find like one element in the set and show that it doesn't hold. So that's basically exactly what's written here. Like there exists an element such that P of A is not true. And likewise for the existential, it's the same idea, but just in reverse. So the existential, when you negate it, becomes the universal quantifier. So here's an example. So let's say we have this complicated proposition. For all G and G, P of G implies there exists a G and G such that Q of G holds and Q of G holds. So how would we kind of prove this? Well, we could break down the same things we had in this slide here and just apply them one by one. So the first thing is that we have this universal quantifier. So we'll just take an arbitrary G. And then we have this implication here. So when we have an implication, right, we assume the premise and conclude the consequence. So we take an arbitrary G, we assume this P of G, and then we this is like our want to show. We want to show this stuff is true. So we have, so breaking down kind of the consequence of the implication here, we have basically something that's, this existential thing here, and Q of G here. So to kind of prove this from our kind of previous slide, what we have to show is we have to show that both things are true because they're conjoined by this and. So we have to show that the this existential is true and this Q of G is true. So going with the first thing, we have this existential, so we can pick any G and show Q of G. And for the second part, we just need to prove Q of G. And in both cases, we have the assumption that P of G is true because we had this implication here. So we get to assume this, and now we want to show this is true. And then we show this is true by breaking it down because it has this and. So we have to show the left side is true and the right side is true. So if we want to disprove this, well, to disprove something, we essentially are proving the negation. So to disprove this, what do we want to prove? Well, we want to prove, we start with the for all. So we kind of negate that and we get an existential. And then we have this G and G such that such that this implication, and we want to negate this implication. So if you remember, if we have like P implies Q, the negation of this would be not Q and P. Because when this is like, if P is true and Q is not true, then this negation does not hold. So in that case, moving on to this, to negate the whole thing, we'd have this P of G and the negation of the right side. So we have this and here. So negating the and, we'd get like an or. And we know that this whole thing is not true, so then it would be like or Q of G. And then on the right side, we want to negate like the existential here. So it would basically be a for all and then not Q of G prime. Which is written right here. So this is kind of complicated, and hopefully you won't have to work with something as long as this. But I just wanted to kind of show how these kind of techniques here would break down, or would break down into, when you're building up a complicated thing, you can break it down into those kind of smaller techniques. And then to prove this, we basically have an or here, so we could prove the left side or the right side. So we could either pick a G and show that P of G is true and not Q of G, or we can pick a G and show that P of G is true, and then for like an arbitrary G prime, show that not Q of G prime is true. Cool. I kind of went by that a little fast because I think the prelim is kind of going to focus more stuff after the quiz. But any questions on that section? Good. Oh, yeah. Yeah.
If we write this stuff on the test, will we at least get partial credit even if we mess up the proof?
Yes. Yeah, so I guess one thing on the exam, I guess this is a good thing to note on the exam. Thanks for reminding me. So on the exam, like on your homeworks, you kind of have to be like very thorough and very precise. And we understand that on an exam, you know, there's time pressure. So kind of the thing you should be thinking of when you're doing a proof on the exam is to basically write something down that is clear and concise and understandable to like another 2,800 student. So you don't have to be like super verbose in your language or writing down tons of sentences. But you do want to make sure you're being clear. And then, like you said, yeah, basically, even if you kind of aren't sure, you get stuck, if you kind of just write things down and show us your thought process, you'll be able to get partial credit. Any other questions?
This. All right, so this is graph induction. So the first thing to note about, can everyone hear me? Perfect. Okay, so when writing graphs, we need to define both our vertex set and our edge set. And so this is super important for questions, even that are asking you to write a counterexample. We want to see the full vertex set and the edge, all the formal set description. And one thing to note here is that undirected graphs are going to use curly braces for the edge set because it's the set and an order doesn't matter. However, directed graphs are going to be using parentheses since it's a tuple and the order doesn't matter. Okay. And what is a tree? So a undirected graph is a tree if it's connected and has no cycles. And vertices with degree 1 in a tree are leaves. And so a cool property that we can use for all trees is that if they have at least one edge, there's at least one leaf. And we should have used this property during homework 4. Okay, so now we're going to think about inducting on vertices with its edges. So for formulating our inductive statement, the most important thing is to decide whether we're inducting on vertices or edges. And this can actually be pretty tricky. So one thing I would recommend is working out small examples, draw out examples of tree or graphs that have the property that you're trying to prove, and see if adding or taking away a vertex or an edge gives you information, because that's the most important thing that you want to capture in your inductive statement. What actually gives you information that will help you solve the proof. So to help with that, we have a couple examples of properties that you might be able to prove. And we're going to go through these, or you're going to go through these and determine whether we're going to be inducting on vertices, edges, or maybe both. All right, so we're gonna take about 5 minutes. Let's discuss with your neighbor.
Every connection. When you remove the edges. I guess you're not inducting. Not induction.
Like the first one I still know. Like it's a shape. You have K plus one. Graph is on.
Same here, and then it's not at.
Three fold. Yeah. Is that every crowd?
Oh, because with grad, like. Yeah, I think we've done that actually.
And it's like you kind of like if you don't have like have like you don't feel like don't feel bad. So I think but when you're it would always be that they're the year, if there was I figured graph it out, cycle, cycle like a cycle. So to adding
Removing edges doesn't really interact. Here we want something, remove something that will.
It's not, yeah, self-connected with other cycle.
Yeah, so. Like, we want something on.
If you look at the circle, you're done. I graph with n versus e is less than n minus b minus one or n minus one. So graph that equals the almost the event equals
Oh, wait, no, like.
what is it?
I'm gonna.
In this case, but like, okay, suppose you're inducting on this added. Yeah.
All right, we're gonna go over these questions. So here is the answers. And so for the first question, we're looking at proving that a graph without a cycle has less edges than vertices, than 1 minus the number of vertices in the graph. And so we want to remove something that will give us information about both the edges and the vertices. In this case, it's going to be the vertex, because we can remove a vertex with degree greater than 1. And that will also, we can also remove an edge at the same time. So we're getting information about both the vertices and the edges. Whereas if we're going to induct on the edges, we don't really have that extra information. And then for every connected graph with n vertices has at least n minus 1 edges, we'd want to induct on the vertices as well in this case. And then particularly for number 3, the trees, in general for trees, to prove that every connected graph with n vertices and n minus 1 edges is a tree, remember that trees are both connected and acyclic. So the acyclic part is very important. And that's why we're using edges. Does anyone have questions about these?
This for number 4, does it assume that there are no cycles in the graph?
No.
Because then it may not be even true. Like suppose I have 4 vertices and I connect 1, 2, 3, 1. So then I have n minus 1 edges and being 4. And I have 1 vertex that's not connected to it.
Sorry, could you say your example?
So suppose I have vertices 1, 2, 3, 4. I connect 1, 2, 1, 4. I mean 1, 2, 2, 3, 1, 3, 1. Then vertex 4 is not connected. So like n equals 4 in this case. Maybe it assumes that there shouldn't be any cycles.
Yeah. Sorry, I will amend that after the session.
Like, how do you when you like how do you guarantee the top to do that? You have to say
Sorry, your question?
yeah, sorry, I was just asking like
Okay. I was just saying in number 2, if like you're removing some arbitrary vertex from the graph, how do you maintain the property that it's connected? Like you have to say something, like you have to assert that that's the case, like you're removing a vertex such that it remains connected, or like how do you assert?
Yeah, so when you're inducting, in your inductive step, you can pick which vertex you're going to remove in a way such that it will remain connected after removing it. So we'll go into that a little bit in the next slide. Or after this. So in homework 4, question 2, we saw the importance of starting at an arbitrary graph of k plus 1 vertices rather than k. So what's going on here? Because when starting at an arbitrary graph of k plus 1 vertices, it really seems like we're going backwards from k plus 1 to k, which can be very confusing. But the key is in the word arbitrary. So when we start at that arbitrary graph of k plus 1 vertices, we already have this arbitrary modifier that we don't have to prove later on. However, if we were going to start at an arbitrary graph of k vertices and then add in a vertex, we have to prove that the graph we create is arbitrary, which isn't always trivial. So you'd have to prove that the method you use to add in vertices to your edges can create all possible graphs, which is a little difficult. And then in the inductive step, you can remove whatever you wish. So for example, in homework 4, we removed leaves and a vertex in a cycle. for choose C. So these were very specific examples of vertices that gave us more information about what to use for the rest of the inductive step. So you don't have to limit yourself to, I'm going to remove an arbitrary vertex. You can remove a very specific vertex in the graph. All right, so we're going to start on a proof. This is true colorability, and it's a property that using only true colors, you can color every vertex in the graph in such a way that no two adjacent vertices share the same color. So for an example, so the coloration on the left is not a valid true coloration because there's two vertices that are adjacent to each other that share the same color. However, the graph on the right is a valid true coloration. So in this proof, we're going to show that every connected graph with n vertices and n-1 edges is two color. All right, so we're going to take a couple minutes to discuss with our neighbors about this proof.
The whole point of this I think you could treat at least for the last. You know what I mean? No, you don't need all that. You can back the graph.
She does that in
And then you basically assume you birth the base case. You have one vertex. Has zero edges. It's colorable because it's just one.
You sort of change the front.
Well, you always assume one. Yeah. You can't have zero. I think I read.
So wait, so was the part I had to do with like after you. I had to make all my own stuff like that. So I was like, oh, that was. You got that last time. We did it when we were sitting outside. One of them, it was harder to figure out. Are you sure? 100%. That there has to be this. Okay, the reason I remember is got the credit on 3 vertices and 2 edges, but
Vertex should be so. You have to use like the theorem that every.
they said which means
I mean, it's possible there's. Wait, so, okay, it could be like. Wait, no, it has.
no, it's just saying like.
So there has to be. But there have to be.
Also.
Or it doesn't have to be a tree, but there needs to be.
Wait, it's non, oh, no, connected graph.
Both would be in like.
You have a cycle n-1.
Oh, yeah, you make it, yeah, just make it.
And
That's because there's an odd number, it's odd cycles. Connected graph is like. What happens then?
A connected graph. Yeah, like you used to.
Yeah, exactly, yeah. It shows like me cycles.
Oh, we If you have a cycle. Well, I think a lot of these things are just to be model, but they force us to screw it. I think 90% of the club.
And they're eight.
What is the? It's usually. So you just say assume it has. It's connected.
So that it has to be. So if it's on a copy,
Right, no, no, all the time.
But you learn. Yeah, you can't have a connected.
If you were to start with the arbitrary graph.
So you.
Full weight to add one edge in order to.
It's no zero thing. Like the theorem is connected graph and n vertices and n minus
No, we don't show it.
and then
Or like. Because like this one is, so like you're.
We normally use the node.
Anything, I didn't say anything.
So when you are wrong, we have nodes and
I'm not sure they. I don't know.
no, they're definitely it's easier to figure out the skill. Yeah, Let's say you connect it to your graph. Really?
So.
And then when you add, make it different, and you'll be, you're adding it.
I don't think it's useful.
No. Like what?
Right?
I think that, it's really.
Some of the, like, focus on one.
Okay. The right institution. What did it say about the number of the degree?
Wait.
I think there's a degree.
That's really exactly.
Yeah, and the fact that there are and.
Yeah. So you could also add.
So it's, I know.
That was always last thought of it.
How do we like?
So.
Might have been something like I think that. You know, I found out, I don't think you guys are driving, those are my hours and.
Yeah.
Like, you wanna go.
Oh, yeah. Like.
Yeah, I have one next semester. If there's something that was like. I'm not. I honestly.
Okay.
Here's a slide change.
Yeah.
I don't know, my purpose involved me saying, we grab the heads, Naples wants to grab. So we need to get down to a grab. So this person on the side is. You do that I did.
Yeah.
You do that I did.
I was thinking it's another technique, you should say that it's connected.
Yeah.
Yeah.
I want to get the picture.
Yeah.
Let's see it.
Yeah.
Yeah, so like the first.
We'll get a soda. We'll get a soda. I need to listen to the explanation. No, I know. Why did they take?
Well, I mean, you.
I'm awake now because of that. Why are you not saying something? It does it, and it says, and they gave it, they gave another basketball game. And it like great. I just thought that was.
I prioritize not to do the grab.
Three players, one player.
But I think that, yeah, the obviously the same. Yeah.
Yeah.
Yeah, and then I had that.
I was actually thinking, I could find. Oh, not mine, not mine. Because we have to make. Yeah. Would have to be 3,000. It's black. Yeah, you can. Our stuff usually. I don't know. So can you do that? Perfect. How we have to speak Spanish? They're not correct. Like, I might like for you, but like, I'll be like, probably already put it on. That's a long time. We don't really have. Question. Yeah. I said, actually, I think I said, basically, point of graph, and in actually there must be two verses, or two verses. So there's no float that I can say where. What I. So. Because I feel often getting a dust on a nose and anyway, that's what's the big difference between when you make it. I'm just saying. Question of okay, what happened? And when you take your and you don't necessarily remove the basket, you mean you just break the connection and like yeah. That's really good. And also make I did rid of the yellow. Okay, yeah.
No, it's not. You have to.
Well, you have to prove it's insignificant because it's like a reason of exactly.
In this case,
It's
then
it's not a significant.
I guarantee you, later this week, there will be like, hey, questions. Like, what's he's gonna say that. He's gonna ask.
And you know what? It's like, no, you know. It's fine. Kind of embarrassing. But no, it wasn't. Why is somebody ask a question? He goes, I oh, it doesn't feel so. Yeah. Well, yeah. Yeah, you still want that one thing. If you build one thing, I didn't say. More likely in our exam that they give us a hint on which one we should know.
Yeah. What's like
It's like really weird and nuanced thing, and it's kind of like.
it is possible.
You don't think so?
Like that.
It's like the strategy. Yeah, really. Counter examples. Yeah, so they did like on out of sight, like it's like I thought. Oh, so I pick up.
But I never heard saying like.
Yeah, design.
I didn't know that there's something. Earlier, and then I was told that's not a good.
Whenever she hears like college, feel like my mom was just like, yeah.
All right, we're going to go over this question now. So does anyone have any idea about what we would induct on, either vertices or edges? Victoria, vertices, yep. So we can set up our inductive statement. Let P of n equals every connected graph with n vertices and n minus 1 edges is true color. One thing to make sure that you're not quantifying n inside of your inductive statement. If we do want to say we're going to prove P of k is true for k in the natural numbers, so you can quantify it during your inductive hypothesis, but do not quantify it within your inductive statement. The base case is that a graph with one vertex is two colorable. We can color with either of the two colors and it will still be two colorable. And then for the inductive hypothesis, we're assuming that P of k is true for k greater or equal to 1. For the inductive step, we're starting with the arbitrary graph of k plus 1 vertices and k edges. So note that it's very important that we're starting at the arbitrary graph of k plus 1 vertices rather than just k vertices. And because, okay, that's kind of weird, but since G is connected and because it's connected and there's k edges, we know that it's also acyclic. So because of that, it's a tree. And there's also going to be exactly at least one leaf, which means at least one vertex of degree 1. And now we're going to remove that vertex V of degree 1 from G to get a new graph G primes. And we use the inductive hypothesis to show that it's true colorable. And now we can add back in that vertex and color it differently from the only vertex that it's neighboring. And we'll have a true colorable graph. And that completes the proof that every connected graph with n vertices and n minus 1 edges is true colorable. Does anyone have any questions about that?
Yeah, my question is just that a lot of sentences had to be written here. So for a timed environment like an exam, what's a way you can make this more concise?
That's a good question. One thing is when you're drawing out your diagrams, your like small examples to try to show it, you can draw out something quick, some like quick sketch of what this process looks like. You can also shorten down these sentences. You can just say like by the inductive hypothesis, G prime true colorable. To say add back in vertex V and color it differently from its neighbor, and really just condense it down to the main idea of what you're trying to convey. It doesn't need to be super wordy as long as you're hitting the main points. Since it's a prelim, we'll be grading a little bit lighter because if you know what you're talking about, that should be conveyed in your proof. Yeah.
So for most graph related induction proofs, you'd have to assume the induction set to be a k plus 1 vertices or edges, and then remove one, prove it's true, and then add back can also prove it's true. That's sort of like the rule of thumb for graph related induction proofs.
Yeah, so you'd want to start on an arbitrary graph of k plus 1 vertices, remove a vertex or an edge, then use the inductive hypothesis to get some information and add it back in. So that's the general proof structure for all inductive graph questions.
This, when you have the k plus 1 case, are you assuming that that's also like all the conditions in the original statement are true?
No,
Are there any assumptions within the k plus 1 case? No.
we are assuming that it's connected. And we're assuming that there's k plus 1 vertices and k edges.
Yeah, that's what.
Yes, so if you have n vertices and n minus 1 edges and it's a connected graph, it's also going to be acyclic, so it will be a tree.
Is that like a lemma lecture or something?
I think it's a lemma in the textbook.
So we're allowed to use any of the textbook as well, not just the
Yep.
So instead of coloring vertex V differently when you add it back, can you also like can you just like choose a vertex V such that it is differently colored from its neighbor?
So you'd have to be very explicit in that. It'd have to be differently colored from all of its neighbors.
But since it already has a degree of 1, can we say that it has a singular neighbor?
Oh, I see what you're saying. Yes, you could.
Suppose you remove vertex V, which is degree 1, and its neighbor is a vertex W, and W is a random, C is 2, and you can't remove V because it is differently colored from C.
Sorry, I'm not really understanding.
Yeah, I think, what I was trying to say was that, like, instead of coloring V differently when you add it back, you choose a V before picking one, so is that neighbor?
It's not. I don't think we're assuming that there's colors assigned to the k+1 graph. Yeah. So like we are assigning the colors. In the, as we go from the k vertex graph to k+1. Does that kind of make sense? Okay, for the sake of time, I think we're gonna move to the next unit, is functions.
Okay, just one more word about what this person said. That's also like an alternate proof. I was kind of like giving that proof out. So if I told you that, I'll make an ed post about it tonight. So you could read about it there. Okay, so now we're gonna be talking about functions. So a lot of the questions we get asked are like, how do I know if I'm writing enough? Like, at what point do I stop writing? If you're asked to provide a bijection or an injection or a surjection, the things that you're going to need to provide, aside from the proof that it is a bijection or an injection or a surjection, is the codomain, the domain, and the actual function mappings. So for the rest of this time where we're talking about functions, all the domains are going to be red and all the codomains are going to be blue, just for the sake of being brief. So there's an example here with constructed sets. So this is X, which contains 0 and 1, Y contains A and B. That's me explicitly defining my domain and my codomain. And then I'm saying that F is a function from X to Y. I could have also said X is a function from 0, 1 to AB. And then I'm providing the mapping. So I'm saying F of 0 is A, F of 1 is B. If I missed any of those three, so that line, let X equal, let Y equal, or F from X to Y, or the mappings, then I would lose points. So you need to have a fully fleshed out domain, codomain, and all the mappings. And then the second example is just a little bit more familiar. So this is from the natural numbers to the natural numbers. And we can briefly describe all the mappings with f of x equals x squared. Does that make sense? Okay, cool. Okay, so now we're going to talk about what a well-defined function is. So a function is well-defined if every input maps to a unique output. So there are two properties that are associated with that sentence. And just so you know, this will be posted, so don't feel like you have to feverishly write this stuff down, but do if it helps you. So totality is saying that for all of the x's and x, there's a y and y such that f of x equals y. So it's basically saying there's no input that doesn't map to anything, which makes sense with like our intuitive understanding of what a function is. Yeah, so that's saying that every input maps to something. So every input has an output. And then unique mapping is saying that its mapping is unique. So it can't map to two things. A function wouldn't make sense, like f of x, if you gave it an x and it gives you, it could be y1 or it could be y2. That's, yeah, that just doesn't work. Doesn't pass the vertical line test on a graph. Okay, so now we have some examples here, and I'm looking for a little bit of participation because these are super quick. So let's look at the top left one. Can we have shouts? Is this well defined? Okay, nice job. Is it not well defined because it's 1, not abiding by totality, or 2, not abiding by unique mapping? Say 1 or 2. Nice job. Okay, now 1 down. So bottom left corner. What about that one? 1 or 2, or do you think it's well defined? So I gave you 3 options. Okay, wait. Is it well defined? Is it violating 1, totality, or 2, unique mapping, or a secret third thing? The secret third thing, yes, it's violating both. So, ooh, I don't.
That's after I was confused by it, but
Okay. I actually don't know how to use that. So it's violating totality because there's one red dot, one red element that has nothing it's mapped to, or nothing, yeah, that it maps to. And then the upper dot maps to 2 things. So that's why it's violating both. Top right corner, is that well-defined? And it's violating unique mapping with that first element. And then the bottom right corner, is that well-defined? Yeah, okay, great job. So I want you to notice, I'm teaching you a method that I don't think has been reported in other ways, maybe via lecture. But this is how I like to think about it. You can always reference back to like what Anka says, what other people say. This is just my way. So when I look at a function and I draw it out in these blobs to see if it's well-defined, I just look at the left blob, so the red circle. And I see if there are 2 lines leaving any dot, or if there's any dot with no lines. Do we see how we can just ignore the blue circle here? Okay. Now we're going to talk about injectivity. So switching gears, a function is injective if each output is mapped to by at most 1 input. So there are 2 equivalent definitions here. I tend to use the contrapositive definition, but we're going to see an example using each of them. So both of the definitions start with for all x1, x2 in X. The first definition is just saying if there are 2 inputs map to the same output, so if f of x1 equals f of x2, that means that x1 equals x2. We could have equivalently written if f of x1 equals y, and if f of x2 equals y, then x1 equals x2. Do we see how those are equivalent? Okay, but it saves you a quantifier, writing a variable. You don't have to write the y. And then the contrapositive is the same thing, but flipped and negated. So that's just true in general. And I apologize for the people in the back who definitely can't read the really small font. But it's just saying the first one is P implies Q. The second one is not Q implies not P. Okay, get comfortable with these. Okay, we're going to do the same thing again, but we're just going to go yes or no if it's injective or not injective. Okay, top left. No, it's not. Bottom left. No. Top right. Bottom right. Amazing. So notice here, so for the well-defined functions, we just looked at the left blob. For the jectivities, which we'll fondly call them, you just need to look at the right blob. So the codomain elements, the blue elements. Surjectivity has a little bit simpler of a definition because it's just so straightforward. Notice that there's no implication here. Some people get a little confused. What am I supposed to assume? There's no left-hand side. When you're proving something is surjective, you're just proving the existence of an element. So I got ahead of myself. A function is surjective if all the outputs are mapped to by some input. So for all the y's, there exists an x. That should be, there exists a lowercase x and a lowercase y, but you get it. Such that f of x equals y. Okay, rapid fire. Top left, yes or no, surjective?
Yeah.
Yes. Bottom left?
No.
No. Top right? Yes. Bottom right? Amazing. So there's the answers. So again, you just need to look at the right codomain blob. So bijective is just the combination injective and surjective. So if you're asked to prove if a function is bijective, you're secretly being asked 2 proofs. So combined with the thing we talked about right before about how to well define a function, if you're asked to provide a bijection, what do you need to give? You need to give a codomain, a domain, all the mappings, that's just for a function, and then prove it's injective and surjective. So writing down all those steps, even if you don't do them correctly, will help you get more points on an exam. This is a little bit self-indulgent because I just like drawing the blobs, but here's comparing some jectivities. So if you get confused easily between injective, surjective, well-defined, not well-defined, I would encourage you to draw out little blobs on your test. The columns are injectivity, the rows are surjectivity. And for both of these properties, we just need to look at the right blob, so the codomain blob. Do we see how that's applicable here? Just looking at the right side. And then our top right corner is our bijective function. Okay, so people will often get confused between well-defined and injective or surjective, and it's because they're really similar. So totality, which is the property of being well-defined, and injectivity essentially are the same property, just one is applied to the codomain and one is applied to the domain. So as long as you can remember which side is which, you'll get them right. Yeah, so that property that they both contain is that there are no two arrows on one dot. So that's either leaving the dot or going to the dot. And the same thing applies for unique mapping and surjectivity. So there are no unmapped dots, no lonely dots. And by dots, I mean elements. So here is a key takeaway. If you're looking at your two blobs, look on the left at the domain blob to see if it's well-defined. Look on the right at the codomain blob to see if it's injective or surjective. Does this make sense to people? What questions do you have about this? Okay. So just to really drive the point home, you can totally ignore what the other blob is doing. And if you're not given your functions in blob form, you can put them in blob form. And that's how you can assess. So who knows what's behind these clouds? I don't care. The upper left is violating unique mapping. I can see that with just looking at the left side. Same thing with the bottom left, violating totality. And then on the right side, we know that it's not injective. Can you tell if the top right is surjective just by looking at that blob?
Yes.
Yes, we can. And same thing with the bottom. So can we tell if the bottom is not injective just by looking at it? Yeah. Is it injective?
We don't know. We don't know,
Why don't we know?
because there could be more dots on the left in the domain that don't have, aren't mapped out.
Okay, this person says because there could be more dots that we don't see. I maybe didn't explain what I drew very well, but the cloud is just covering up anything that was in the domain, but all the arrows are still like, that's all the arrows that there are. So barring the fact that it could like not be a function, this is injective because no two domain elements are mapping to the same code element. Okay. So here are some general strategies about proving an injectivity. So as we said before, there are two definitions. There's the contrapositive and the non-contrapositive one. It's kind of tricky to know which one to use. It just depends on the amount of information that you have. So pick whichever one you end up using more, commit that to your memory, and then you can always easily find the other one by just flipping it and negating it, right? So if you're starting a proof and you're having some trouble working through it, you can always try to switch to the other definition to see if you'll have more luck there. And remember that both those definitions are implications. So what Stephen was saying earlier about proving implications, you're taking an arbitrary element and making it so that the left-hand side is true. Using the fact that the left-hand side is true, you want to show that the right-hand side is true. And then my final strategy is to write out the definition somewhere to reference and to keep yourself on track. This also is helpful for you if you make a mistake, because then we as the TAs get to see, oh, you know what you're talking about. Maybe you just wrote a Y instead of an X or something like that. So this is just the general form of how you can set up the injectivity proof using the contrapositive definition. So I very controversially wrote that you should define it at the beginning. Ambrose would say you should define it at the end. Both are completely valid. Just have it somewhere. So yeah, I'm gonna say define it at the beginning. You can define it at the end. Do whatever you want. Just put it in. So I first write out my definition. We want to show, WTS want to show, for all x1 and x2 in X, that if x1 does not equal x2, that means f of x1 does not equal f of x2. So again, that's just going to help you stay on track and also show us that you know what you're talking about in case you made a mistake. The next part is the most important part of the proof, arguably. Maybe the third is actually, but still. You want to assume that you have arbitrary elements on the left-hand side. This is maybe like the most common mistake that people make. They write out the definition and they think that that's the same thing as taking arbitrary elements. There is someone in this room that will make this mistake on the exam. You have the power to let it not be you. So don't skip this step. You probably should have the word assume. If you don't, take a step back, reevaluate. Does anyone have a question as to why you can't use just number 1 and skip number 2? Okay, I believe you. Part 3, you want to actually prove it. So you're using your assumption. So you've assumed that the left-hand side is true, that left-hand side that we wrote up in the definition. We're assuming that we have those 2 values, x1 and x2, that are not equal. And now we're going to apply f to both of them. So we're going to have an f of x1 and an f of x2. We're going to be given what the function does. So apply that definition to them and then use that, simplify it to get to 2 final values and then show that those aren't equal to each other. Then in your conclusion, if you wrote the definition at the beginning, you can just say this generalizes for all the x's and x. It's injective. If you didn't, you should explain why it's injective. So we have shown there, for any 2 x1, x2 such that x1 does not equal x2, then f of x1 does not equal x2, which means that it's injective. Okay, so now we're going to work on a contrapositive injectivity proof together. So this proof is to show f from z even to z odd, where f is defined as f of x equals 2x plus 3 is injective. Try to use the contrapositive definition, which is up here. If you need a second to write it down, feel free to. Okay. I'm moving it away now. So our first step is going to be define it. There it is. You can define it. So this is like that general hypothetical property about it. Remember, at this point, we have not assumed anything. We don't have arbitrary values to work with. If we didn't write another assume for the rest of the proof, we would be getting points off and we'd be doing it wrong. Don't make that mistake. Okay, so does anybody want to be brave and raise their hand and say what we should assume is true?
Just take x1 not equal to x2.
Exactly. So we're gonna assume we have an arbitrary x1 and x2 in z even, and we're going to, or arbitrary x1, x2 and z even such that x1 does not equal x2. So there it is. I also added in some sauce because they're even. We know we can write them as 2k for different k's because they're not equal to each other. So I'm going to say x1 is 2k1, x2 is 2k2. And then now is the actual prove it step. So here's where we're going to apply the function definition. Before I go to the answer, try to imagine what that step is going to look like. What happens when you plug in x1 and x2, which is 2 of k1 and 2 of k2, into f of x. This is what happens. You apply it, you get to these 2 equations. So 4 of k1 plus 3 and 4 of k2 plus 3. We know that k1 does not equal k2. So I did a little for the sake of contradiction. You could also prove this directly. But we're just going to say because k1 doesn't equal k2, that means that f of x1 doesn't equal f of x2. And that's our contradiction that we've arrived. So we know that, yeah.
So for a defined step, should it be x1 equals x2? If that's true, then f of x1 should not be equal to f of x2.
So yeah, I did a contradiction proof here. So I'm saying for the sake of contradiction, assume that they are equal to each other. So I, at the beginning, said that the x's aren't equal to each other. At this point, after reading the for the sake of contradiction sentence, what we have in our minds is, okay, this proof is saying that x1 does not equal x2, but f of x1 does equal f of x2. So like another way to say this is like, for the sake of contradiction, assume that it's not actually injective, but we know that it is. So does that make sense, using the contradiction?
Sorry, could you explain like what for the sake of contradiction means?
Yeah, for sure, for sure. Okay, so you want to show P implies Q. this doesn't just apply to functions, this applies to any proof in general. You want to show P implies Q, assume P, that should always be your first step. And then you can either directly show that Q is true, or you can show like, it wouldn't make sense if Q wasn't true. So like in all possible cases, once we've assumed the left side, Q has to be true. So for the sake of contradiction, like I'm about to lie right now, I'm going to say Q is true, just so I can show you how wrong that is. So what you do is say, for the sake of contradiction, assume, not Q. So what is our not Q? From our definition, we can reference it so easily because we already wrote it. We want x1 not equal x2 such that, or implies f of x1 not equal f of x2. So our P is going to be x1 not equal x2. Our Q is going to be f of x1 not equal f of x2. So we take not Q, which is that they're not equal, which means that they're equal.
How do you do it the other way? Like not using single contradiction for this specific problem?
So to do it the other way, not using contradiction, you can just directly show 4 of K1 plus 3 does not equal 4 of K2 plus 3. So you can reason about, well, we know K1 does not equal K2 by our assumption. So we know that 4 of K1 does not equal 4 of K2. So we know that 4 of K1 plus 3 does not equal 4 of K2 plus 3.
So could we have just done this same thing like with the X's instead of the 2 Ks?
You could have done the same thing with the X's instead of the 2 Ks. There's a bit of motivation to show that it's in the even numbers and that the output is going to be in the odd numbers. To fit it on this slide, I actually took out the sentence that was like, notice that these are both odd, like 4K1 plus 3 and 4K2 plus 3 are both odd. You probably would want to say that in your explanation.
Just confirm the original statement before the contradiction would be if x1 equals x2, then f of x1 must not be equal to f of x2. And then taking a contradiction, you would prove that the contradiction can't be true, and therefore the original statement is true.
Yeah, so if I understood your question correctly, when you take a contradiction, the thing that is the contradiction is your assumption. So you're assuming something that's not true, and you're going to work with that until you get to like something that just couldn't possibly happen. Like, for example, it can't be that 4K1 equals 4K2 because we know K1 doesn't equal K2.
Would it be fine to use to prove this not using the contrapositive definition and kind of not assume that they're distinct arbitrary values and then apply the function each and show that implies that those arbitrary values are the same value?
Yes, okay, so this person said, is it okay to not use the contrapositive definition? It is okay. I leave that as an exercise to you to do on your own. And we're going to do an example in about 5 minutes of using that definition. Any other questions before I move on? Keep them coming. Okay. Okay, and then there's our conclusion. Since x1, x2 are arbitrary, this applies to all of the x's in Z even, so F is injective. If you were doing it a different way, this might be where you use your definition. And just for people who want to do it that way, it might help you to write the definition all the way at the very end as your first step. You might like do the proof from the bottom up then. Okay, so this is what this person was asking, a direct injectivity proof. So it's going to start the same way. You define it, but this time we're not using the definition with the not equals. So remember, we have those 2 equivalent definitions for injectivity. Some of these hints are kind of the same thing. This will help you refer back to it. It will help us, help your grade, write it down. And now you're going to assume that the left-hand side is true. So in order to assume that the left-hand side is true, we need some x1 and x2 to work with. So that's when we say, assume we have an arbitrary x1, x2 such that the left-hand side is true. That should be equals, not equals. I'm sorry if that's confusing all of you right now. Number 2 should be equals. Okay. Noted. So please do this step. If you don't do this step, it will be very disastrous for your grade. 3 is prove. So you have this assumption that f of x1 equals f of f2, f of x2. And now you want to show that x1 equals x2. So f is going to be well defined for you. It might be like an algebraic thing. It might be like a set thing. You're going to use that definition. So plug in the definition and then simplify it until you get x1 equals x2. And then you make your little conclusion. This part is maybe the least important unless you didn't write the definition above. Show that it generalizes. Write the definition there if you didn't write it before. Does this make sense for people? Okay, we're going to do a simple example. So f is defined from n to n. We want to show that f of x equals 6x squared is injective. Okay, try from memory right now to write down the injective definition, the direct one. So there's no not equals in this one. Okay, so I have it here. This is the first step. We're going to want to show that f is injective. And that means that for all x1 and x2 in n, notice how I say n here and not x. We could have said x, but we had a more specific definition. We knew what x was, so we just plugged it in. So we want to show that if f of x1 equals f of x2, that means x1 equals x2. Okay, so who wants to be brave and say what we're assuming? Yeah, so x1 and x2 exist in the natural numbers. And then also that the left-hand side is true. So there is an f of x1 or there is an x1 and an x2 such that f of x1 equals f of x2. Great, there it is. That's exactly what we just said. And now we're gonna prove, okay, I'm flashing it for you here now. Okay, now try to invent it for yourself. Take like 30 seconds just to write it out. Use the definition 6x squared. Okay, we're gonna show it now. So for the other way, the contrapositive way, we added the definition of f. Like we applied f to x1 and x2. Here, we're gonna try to like strip away the definition to get to x1 equals x2. So we have f of x1 equals f of x2, only if, or if and only if, 6x1 squared equals 6x2 squared by the definition. We divide by both sides, and then we get this step. So when we take the square root of both sides, how do we know that that doesn't like break our proof?
Numbers?
Natural numbers, yeah. So what's not in the natural numbers? Negative numbers, exactly. So would this proof have been true if the codomain was z, so the integers? No, it wouldn't have been. Yeah, therefore f is injective. Oh-ho. One step ahead. It's not true. Why? Because of those negative numbers. So to prove a property doesn't hold, you just need to provide one counterexample. Don't waste your time trying to write a generalized proof. It's not necessary. Can anyone think of two x's where f of x1 equals f of x2, but x doesn't? Yeah.
-1 and 1.
-1 and 1, like you read my mind. -1 and 1, that works. So it's just any two numbers where those two numbers squared equal the same thing. So the negative and positive version of the same number. So here, this is my entire proof. Notice it's 3 lines. That could be you. So consider x1 equals 1, x2 equals -1. I plug it in. So f of x1 equals f of 1 equals 6 times 1. F of x2 also equals 6 times 1. They both equal 6. But 1 does not equal -1, so it's not injective. Any questions about this? Okay, here's some general proofs for surjectivity. So remember, this is that there are like no lonely guys in the codomain. So everybody is mapped to. So we're just trying to prove that the x exists. So we start with a y, and we're going to say, I'm going to find that x that maps to y. So the most common mistake that people do here is they preemptively start using the X. They're like, well, I know Y is in the codomain, so I'm gonna call Y f of X. Where did the X come from? You need to prove the X exists. That's the whole point of surjectivity. So don't use X until like basically you're done with your proof. And then remember to show that your choice of X actually satisfies f of X equals Y. If it's extremely complicated, then you don't have to do that. Yeah, but we won't give you an extremely complicated one on the test. Okay, so here's the like general structure of it. Notice how these are all really similar and maybe have the same bolded words. The first is to write out the definition. So it's just saying if I have a Y, then I have an F, or then I have an X such that f of X equals Y. The second is assume. But here we don't have a left-hand side and a right-hand side. So we're just assuming that we have an X. This is where you get to be like a little forward. You can just claim what the X is. You in your head are gonna do some math, figure it out. You could write it down if you want, but all you have to do is explain what the X is that satisfies that. So given a Y, find the X. So I claim that X satisfies this because blah, blah, blah. And then the blah, blah, blah is gonna be the show f of X equals Y. So that's plugging that X back in, seeing how it evaluates to Y. Oftentimes, maybe almost always, the X will be in terms of Y. So yeah. And then make your conclusion. Again, if you didn't write the definition above, you should write it below. Okay, so here's a surjective proof. We want to show that r squared to r squared f of x1, x2 equals x1 minus 1, x2 over divided by 7 is surjective. Does anyone know another way we could say r squared?
Real numbers in like a tuple, like
Two real numbers in a tuple, that's correct. Does anyone else have another one? R cross R, yeah, so the Cartesian product of R and R. I'm just gonna write that on the board. That's what it means. And it's a pair of two real numbers. So the input to F is gonna be two numbers. The output is also gonna be two numbers. They're both gonna be real. Okay, try to write down the definition. I'll give you like 10 seconds. This one's a short definition. So I want to show for all y1, y2 in R squared that there exists an x1, x2 in R. That should be squared. That should be squared. Such that f of x1, x1, x2 equals y1, y2. So don't get confused. The first R squared is going to be in the domain, and the second is going to be the codomain. Oh wait, I flipped that. The y's correspond to the codomain. The x's correspond to the domain. And yeah, that should be R squared. Okay, so what is our assumption going to be?
just x1 and x2.
So there's one school of thought, which is that there exists an x1, x2. I was calling the x1s and x2s the elements of the domain. Do we want them to be elements of the domain or codomain? Enthusiasm, guys. Codomain, yeah, codomain. So if you call it x1, x1, x2, that's totally fine as long as you specify that they're in the codomain. So I called them y. It's totally fine to call them x if you really want to. So we have our outputs. We want to find the inputs that map to those outputs. Notice they're tuples. I could have called it x and y, but then x and y would be tuples. Any questions about this? Okay. So, okay, now you can find the x. Your sentence could be, I claim the x that satisfies this is blah, blah, blah. You could just say, consider x equals blah, blah, blah. Spend like 30 seconds, try to find it. It was a mistake. It should be R squared. Yeah. Thank you for asking. Share what you think with your neighbor. We appreciate that you guys are fighting the urge to disengage. We know this material is long. The prelim is stressful. Try your best.
Yeah.
Does anyone feel really confident about their answer and wants to share it? Okay. Make like eye contact with me if you have an answer, but I won't call on you. I just want to know. Okay, amazing. We all have answers. So my answer was that x1, x2 equals y1 plus 1 and 7y2. So I got this by reverse engineering the function definition. So here's my proof of why this works. So I'm gonna apply f to both sides. Well, not both sides. I'm gonna apply f to both elements. So there, the second line, I'm just substituting in what I defined them as. The third line, I'm using the definition of x. And from the third line to the fourth line, I'm just simplifying with algebra. So our conclusion is that since y1, y2 is arbitrary, this applies to all the pairs in Y, so F is surjective.
That any number minus 1 is also a real number, and any number divided by 7 is also a real number.
Yeah, that's also true. So we know that the codomain is also real numbers, but do we know that it maps to all of those real numbers, or do we miss one? And this is our way of saying, we know we're not going to miss one because here's a random one. We don't even care what it is. We can find the X that maps to it. Okay, before we go to relations, I'm just going to say a quick thing about inverses. So this I'm just going to write on the board. So given any function from a domain to a codomain, it's invertible if there's a function from the codomain to the domain that you can apply that undoes the function. So there are like left and right inverses. It's invertible if it has a left inverse and a right inverse. It depends on if you apply the inverse to the left side or the right side, right? So there's also another fun fact. It's that if a function is bijective, it's invertible. And if it's invertible, it's bijective. So that means it is bijective if and only if it is invertible. So theoretically, if we ask you to find a bijective function and you can find the inverse and prove that it's the inverse, that would be a proof that it's bijective. But we probably will ask you to prove that it's surjective in native. Do people have questions about inverses, or should we move on? We're kind of pressed for time. Would anyone benefit from me writing out the definition? Okay. 1 second. I used C's and D's for both the element and the set. So the lowercase c and the lowercase d represent these little elements of C and little elements of D. So we have left and right inverses. If we have both, that means it's invertible, right? Actually, wait, they should be and because I wrote that it is invertible. Okay, do people have questions about these definitions? Okay, great. So now we're gonna move on to the next topic.
Flip the X and Y.
All right, I am not going to be using the slides, so I'm going to be handwriting everything. If you can't see what I write or it's like illegible or too small, please just yell out. I'll try to make sure that doesn't happen, but yeah, do let me know. So we're going to be talking about set cardinality. So way back when you were young and naive, we told you that the cardinality of a set is just the number of elements in it. Unfortunately, that definition doesn't really work when you get two sets that could be infinite. And that's kind of what we're dealing with now. So when we talk about the cardinality of a set, we say that, for example, the cardinal, not going to use green. The cardinality of a set A is less than or equal to the cardinality of B if there exists an injection F from A to B. Likewise, for if we use greater than, it's the same thing, except it's a surjection. And if it's equals, we use bijection. So all the stuff Robyn was just talking about, you can't forget it. It's still important. We're going to be using that in just a moment. So in general, if you ever see a question on an exam about asking you to show that the cardinality of one set is less than or equal to the other, do not start talking about the number of elements in them. Think functions. You're going to have to come up with an injection, surjection, or bijection, depending on the problem. So for one problem, I'm going to define this set F to be the set of all functions, little f, such that f goes from the set containing 0 and 1, the natural numbers. So first off, start reasoning about what this actually means. What is one element of this capital F set? And then what is going to be the cardinality of this set? So just take like a minute or so to think about what the cardinality might be. Is it going to be finite, countably infinite, uncountable? Who knows?
It's a plan. It's a plan. Yeah. I actually zero. Finite, we're counting. We can enumerate it.
So instead of all functions,
Writing that information.
every element.
No, that's showing something that's.
Yeah, I think we just said it.
Oh, no, yeah, things that, yeah. Yeah. Set containing function.
So less than means that it's there's an injection here.
Yeah,
like
that-
not a bind. Injection and not a surgery.
I would believe.
Sorry, there is no surgery. There is no. That says there's an injection. That one says there's an injection, but there is not a surgery. Yeah.
Wait, that's it.
Because like, you can think about it again, like the equal sign means there exists a line.
Oh, it's.
So if you remove.
I think it's. It's kind of. It's so I use. I think it's kind of.
It depends, like, if I care, try to say, that was specific. The sake of the question, we're not to do it. It's less than- Not. That's not related.
Yeah. So if this.
I don't like it. You sound sure. Sound sure. Like, you sound too sure.
All right. You hear me? Don, yeah, okay. We're gonna first just consider what is an element of this capital F? Like, what does one of these things look like? So it's the set of all F such that F is a function from